Okay, so I'm briefly just gonna explain some of the points that are not written. For example, in this summer 2019 exam 2 that was done by some students last year. So characterize the following reactions as substitution reactions, elimination, addition, or rearrangement. So for the first one here, what I would have done if I were you, I would have shown all the hydrogens possible, because I really want to know if I've taken them out or I've added them. So in this case, I've shown all my hydrogens. Let me change some thickness here. I've shown all my hydrogens, and then coming here, I have the two hydrogens all over the place. All around this ring, you have the hydrogens all around these rings. Okay, so you definitely see that hydrogen was added. Now, because hydrogen was added, this is an addition reaction. That's an addition reaction. So for the next one, you see, if you compare the starting material and the product, you see that you're making a double bond. I gave you the clue that each time you see a double bond in a product, that most likely means that you did elimination. Okay, so the alcohol here, the OH group must have been lost. You have two hydrogens on here. Okay, so I would say that this OH is taken out, this hydrogen is taken out. That's how you make a double bond. So you see this water here that's lost. So when water is lost as a product, it means you eliminated it, you removed it. Okay, so this reaction right here is an elimination reaction using an acid catalyst. Okay, so next on part C, you have an alcohol still, but this time I don't see a double bond that's formed. So instead, what I'm seeing is that this hydrogen was taken out and something else replaced it. So if you're looking at replacement, then you must be doing substitution. Now, we don't know whether it's SN1 substitution or SN2. That will be covered later. Okay, so now you see that that's a substitution reaction because one group was replaced by another group. Okay, and of course you see the clue here, it says two equivalents. That's why you have the two rings bonded. I know water was lost here. That's not an elimination. Elimination should give you double bonds. Okay, so next, I see the same number of carbons. If you draw the hydrogens, will be the same number of hydrogens, but look, the plus sign is now on another side of the structure. So we moved it, so we must have rearranged the molecule. So specifically, this is called hydrogen shift, which is part of what's going to be tested in exam 2. So usually you want to move a hydrogen from a more substituted neighboring beta carbon. This is more substituted than that. You have more carbons on this carbon than on this carbon. So you move this hydrogen here. You're stealing a bond from that carbon. It's one bond less. That's why you have a positive formal charge right there. Here you had one hydrogen. Now you have two of them. So you shifted it, you rearranged it. Okay, here I'm not going to say we are making a double bond. We are just moving the double bond. Again, it's a shift of the position, so it should be a rearrangement. Mechanistically, if you want to see this, let's say this hydrogen is taken out by the lone pair of the nitrogen, and then you make a double bond here, and then this pi bond goes to replace the lone pair that was used to make a HN bond. So now no element is lost, no atom is lost, the number of bonds are the same. It's a rearrangement. Here we started with 2 reactants, you end up with 1 reactant, so you fused them together, so you really did an addition. So that's an addition reaction. And the way to look at it, the lone pair is just gonna attack this partially positive carbon, and then this pi bond opens up. Okay, here I see the double bonds to the left, the double bonds are to the right. So again, I will take this as a rearrangement. Okay, very simple, 21 points on that one. So to show your mechanism in this question as it asks for, I told you always try to start from the lone pair. If the lone pair is not there, then start from the pi bond of the double bond or a triple bond. So in this case we have a lone pair. Just start from the lone pair and use the lone pair to attack the positive center. Remember, electrons are negatively charged. This is an acid, H+ is a proton. Opposite charges attract. That's why we are able to push a mechanism. The double-ended arrow implies you are moving 2 electrons. Because you use the lone pair, the oxygen gets a plus sign. It's left with 1 lone pair. Okay, so to show how you make this product, that's the arrow. To show how you make this molecule, you simply lose water. So what was needed to be shown on the end, let me scroll down and go back where we were discussing. So what's needed to be shown on the end here is water molecule that fell off. It's gonna fall off as a leaving group. Okay, simple mechanism. Here, which of the following carbocation cannot undergo a shift to be more stable than before? So for this class, you want a tertiary carbocation over a secondary carbocation over a primary over a CH3+. The reason is how stable the carbocations are whenever they are more substituted. So let me put a plus signs here. Tertiary must be more stable than secondary. Secondary must be more stable than primary. Primary is more stable than methyl carbocation. So just to give you an idea on why the tertiary is more stable than the secondary. Okay. So this is tertiary because you have a carbon, 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 3 carbons bonded to C+. So it's tertiary. This is secondary because the C+ is bonded to 2 other carbons. So the reason why this is more stable is because you have electron donation through bond, inductive effect, stabilization. Otherwise, we explain it in terms of a fancy word, we call it hyperconjugation. So you have these arrows pointing towards the carbon. The same arrows will be in DCH3. The same arrows will be in DCH3. You definitely see a lot of contribution towards the C+ compared to where you only have 2 CH3s. So much of the positive character, positive charge quenching is affected on tertiary compared to secondary. So that's why tertiary is more stable than secondary. So now let's see which of these cannot undergo a shift to be more stable than it were before. So this is a secondary. I can move a group from a more saturated neighboring carbon. Again, I told you that's a butyl carbon. This is primary carbon right here, and this is a quaternary carbon right there. It's a carbon bonded to 4 other carbons. So you move a group from the quaternary. If you had a methyl and hydrogen, you move the hydrogen. It's easier to move the hydrogen than the methyl, but here there's no hydrogen, so we'll move one of the methyls. Draw what you're gonna end up with. Okay, so you see I end up with a tertiary carbocation. The C+ is bonded to 3 other carbons. Here, this is a secondary because the C plus is bonded to 2 other carbons. So, okay, this can do the carbocation shift to be more stable than it were. Okay, that's a secondary carbocation, tertiary carbocation. This should shift. And this kind of shift is a metal shift because we moved the CH3. The CH3 ends up there. I forgot to draw it. So that's a tertiary. Now here, you're starting with the secondary. Again, the C plus, this carbon plus, is bonded to 2 other carbons, so it's secondary. But we need to see if we can shift and make it tertiary. Of course we can. Here there's a hydrogen, so I'd rather move a hydrogen with the bond and not the metal. Like I said, it takes less energy to move a hydrogen. So you already have 1 hydrogen here that makes 3 bonds to the carbon. So when you move the other hydrogen, you have 2 hydrogens, the plus sign is gone. So now the plus sign will be here. It's like swapping position of the hydrogen and the plus sign. So this is a tertiary. So this should do a shift. Same thing here, you can do a hydrogen shift from the more substituted neighboring beta carbon. In doing that, you're gonna end up with a tertiary. You started with a secondary, so this should do it. This one will not, because see, if you try to do the shift, which only happens once, you don't do too many shifts, you still end up with a secondary. So that's why this one cannot undergo a shift to be more stable than it was. So next, question number 5. Classify the following as chiral or achiral. Now, chiral means there is no internal plane of symmetry, there is no center of inversion. We covered that. In other words, there is no center of inversion already. And you also have for chiral carbon, you also have at least 4 different groups on a carbon. 4 different groups on a carbon. Okay, so now let's start with the other one. So a chiral is simply the opposite of the opposite of chiral. Could have one of these conditions, one or more of these conditions forfeited, one of these conditions not followed. So this carbon right here is not chiral. It's not stereogenic. It's not a chiral center because you have 2 methyl groups that are the same. Remember, this is a CH3. That's a CH3. So that center right there is a chiral carbon, which means this is also which means that carbon also does not have 4 different groups because you have 2 metals that are the same. So overall, this molecule is achiral. It lacks 4 different groups on none of the carbons on the structure lacks 4 different groups. That's what I want to say. Here, there's no way you can cut and get symmetry because this metal is away, this is towards, or definitely if you cut this way, they are not reflecting because this is up, this is down, or this is towards, that's away. So that's not a center of inversion or internal plane of symmetry. There's no internal plane of symmetry this way, and I have carbons with 4 different groups on them. If you draw the hydrogens, you will see that going this way is different from going that way, and it's different from the metal. So this guy is truly chiral. It's obeying all those checkpoints. And then this carbon right here is a stereogenic center, which means you have 4 different groups. I would consider it. This one has 4 different groups. I would consider it. There's no center of inversion. There's no internal plane of symmetry. That's chiral. This guy is achiral. I think we did such a molecule in class, and I told you the best way you can see it is to draw the 2D. So that's down and this is up. So you already see that I can cut this molecule into equal parts. Simply put, I will take I'll take this as the internal plane of symmetry, cut into the carbons through the hydrogens. You know, these carbons, hydrogens are just spherical in shape. It's just that some are bigger than others, like an orange and a basketball. So you see this side, the left side, is reflected onto the right side. This molecule has internal plane of symmetry. And because it has internal plane of symmetry, the molecule turns out to be a chiral. This one is chiral. There's no internal plane of symmetry, and you have that carbon right here with 4 different groups on it. This one is achiral because there's some symmetry. You know, I did not write here CH3, but it's really there. So you can see that you can cut this into equal half. You know, this is just a bond going this way, but really it could be going through this screen. So I can cut it into half. So definitely this part is reflected that part. In other words, this carbon right here does not have 4 different groups because this is the same as that. So this compound is achiral. You just need to practice and practice and practice these things. Don't tell yourself you got it. You have to practice, and after practicing, practice one more time. After practicing one more time, practice over again. That's how you get to be a master of these things. So what's the relationship between the following compounds? Are they enantiomers? Are they diastereomers? Are they what's the other one? Are they identical? So if they are meso, they would have internal plane of symmetry. If they are diastereomers, then you're looking for one stereogenic center kept, the other one is switched. If they're enantiomers, both stereogenic centers must be switched, and there is no internal plane of symmetry. That's the overview of what these terms mean. Okay, now here I look at the molecule, compare both of them, and I'm telling myself, my eyeball can't really tell me what's going on. So let me try and assign RNS. Hydrogen will be priority number 4. Okay, now we are left with carbon, carbon, carbon across this stereogenic center. So this carbon will take 1 because it's bonded to more carbons, or it's more substituted. Now coming here, CH2, CH2, I can't tell who wins, so I go 1 bond further. So this carbon is bonded to a carbon. This is also bonded to a carbon, but the difference is going to be on this one. When you go 1 bond further, so I could say this wins over that. So which means this whole bond wins. So that gets 2 and this gets 3. So I'm looking at 1, 2, 3. I'm going S, but the problem is my smallest group is towards me. The true assignment for that chiral center should be an R. So let's give it an R. It's not a good color to use, Moses, too bright to the eye. So let's use an R for that one. So once you assign that one, you assign the next one. I can delete this. If you want, you can pause the video and rewind and see what I wrote. So this will be 1. Obviously the hydrogen is towards you, is 4. Then going this way you meet the isopropyl, going this way you meet the methyl. This should be 2, this should be 3. You're going 1, 2, 3. We are going R for now, but the smallest group is towards you, so the true assignment here is an S. Now we are here on the methyl. I'm gonna clean up again. Okay, let's see. Carbon to CH3, nope, that's not gonna get priority. This CH3 will be number 3 definitely. And then let's see, I'm just trying to counter check and make sure I did it right. Okay, those are correct. So this bond going to isopropyl, this bond going to isopropyl. So this is not, this carbon right here is not a stereogenic center, because I see that I can split this carbon into 2. This side is the same as this side, so no need to give it chirality. So let's do the chirality of the other isopropyls. Okay, so here that's 4, so this is 1. Going to the isopropyl is gonna be 2. Going to the methyl will be 3. So I'm going 1, 2, 3. I'm going R, so I keep my R because the smallest group is at the back. Here, we clean up. This gets 1. Going to isopropyl bond gets 2. Going to methyl gets 3. Smallest group is towards you. So I'm going 1, 2, 3. That's an S. It is an S, and the smallest group is towards me. The true assignment is an R. Okay, now let's compare. You have RS and you have RR. So one stereocenter is kept, the other one is switched. That's stereomass. If both of them were switched on the other molecule, it would have been enantiomass. Okay, again, I won't worry about this carbon center, because if I split it into 2, I will see that I have same substitution on the left, same substitution on the right. Regardless of whether they are up and down, it does not matter. You have the same elements on the left and the same elements on the right. So that's not chiral center. Okay, so that's why I did not assign it chirality. So here, this is an ethyl, and that's an ethyl. This is an ethyl, you have internal planar symmetry, you have internal planar symmetry. These guys are identical. No need to assign chirality on both. Here, this is not a stereogenic center. You have 2 methyls, which is the same group on the same carbon. No need to give RNS. So I move over to the next carbon. Chlorine gets 1. Obviously, this carbon right here is more saturated than that. This is a CH2. And of course, that has 2 metals. So I'll give this number 2 and I'll give this 3. Smallest group is towards you. So I'm going 1, 2, and 3. That is an R. Smallest group is towards me. So the true assignment is an S. Again, I don't need to care about assigning chirality there, because I have the same 2 methyl groups. So this is 1, that's 2, that's 3. So I'm going 1, 2, 3. So I'm going S. Smallest group is towards me. Right? Here we are going S, counterclockwise. Smallest group is towards me, so true assignment is an R. So that's why the answer is enantiomass. The chirality is switched. I don't have internal planar symmetry. There's no center of inversion and all that. Okay, practice. Just practice, practice, practice. You guys, practice. Make time and practice. Practice, 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 practice. Okay, so here we are looking at amoxicillin. You guys, I think you might be knowing what amoxicillin is. It's an antibiotic used to treat a number of bacterial infections. So it's an antibacterial drug. So this include middle ear infections, streptococcus, throat infection, pneumonia, skin infection. You go to pee and you have trouble. This guy, the doctor's physician might give you to use. So anyway, we are not treating any patient here. All I needed here is for you to identify the chiral centers in part A. Carbon chiral centers, because they could be nitrogen chiral centers, but I'm focusing on carbon chiral centers only, carbon atoms. In this case, if you mark too many, or if you say the number is 10 and I really was just looking for 9, you lose points. Anyway, sp2 carbon, I won't consider it. I won't take it to have 4 different groups. We talked about that in class. So all these carbons in the benzene ring, I don't consider those. There's a hydrogen here. You have nitrogen, you have a carbon, sp2 carbon, sp2 carbon to carbon, sp2 carbon to oxygen. This is one of the candidates. 4 different groups. That's what I'm looking for chiral centers, which means you have 4 different groups. That's a nitrogen, is not a carbon chiral center. So this one also have a hydrogen. There's no internal plane of symmetry. You have carbon to carbonyl, carbon to sulfur, and nitrogen and hydrogen. That's the other one. And then here you have a hydrogen, a sulfur, a nitrogen, and a carbon. Definitely that's the other one. This is not, because CH3 and CH3 are the same. This one is another candidate. You do have a hydrogen there, because I see 3 bonds. I know there must be 4 bonds. Carbon has a valency of 4. So in this case, you have 4 stereocenters. N equals to 4. Usually the follow-up question that comes is how many stereocenters can be drawn from the general structure of amoxicillin above. So you punch in your calculator, use the formula 2 to the power n, n being what you just answered on part A. So we have 4 stereocenters, 2 to the power 4, so the answer is 16 stereoisomers possible. Like if you put wedges on here, there are 16 ways you can show the wedges towards you and away per bond. Good luck drawing all possible stereoisomers. So next one is chairs. You are required to draw the ring flip. And in fact, I'll do a follow-up question and ask you which of the 2 chair conformations is the most stable. So let's do the ring flip. Usually the first step you want to do is to actually draw the opposite of the parent chair. And then label it accordingly. A, B, C, and then I have D right there. So the A has a bromine up and equatorial. After the flip, the bromine should go up axial. So only equatorial and axial change. The up stays. The isopropyl that was axial down should end up equatorial down after the flip. So I'm just trying to draw this answer here. So on C you have OH axial down. Okay, so after the flip I expect it to go equatorial down. Now remember, these bonds must be parallel to the bond across. Like this bond is parallel to this. This must be parallel to that. I mislabeled my D. Let me put D where it's supposed to be. So bond C to the OH. This bond, OC bond, must be parallel to bond ED, right there. So equatorial down. So on D I have a methyl down. That methyl, I have methyl on D here. I have methyl equatorial down. So after the flip, it should go axial down. Let me use a green pen to draw axial down. So axial down, something like that. So it's this method right here. So that's how you work your chairs. The ups and downs stay, but equatorial and axial switch. Circle one of the Newman projection. Oh, before we do that, the follow-up question is usually which of these two chair representation is the most stable. You want to go with the one that has the most big groups equatorial. So I see bromine equatorial, methyl equatorial. Here I have bromine isopropyl equatorial, OH equatorial. Let me see, is it possible to ask for stability? Here it's hard to tell because who is bigger? It's hard to tell between Br and isopropyl. I think isopropyl causes much sterics in space than the bromine, so I would say the most stable one should be, in this case, should be this, because in both of them I see two axials. OH is axial, isopropyl is axial, Br is axial, methyl is axial. So usually you want to go with the one that has the least axials, but these two guys have equal axials. So if they have equal axials, then what you're gonna look for is which one has the bigger group equatorial out of the two. So that's why I'm thinking the one that has the isopropyl on equatorial position would be the most stable if asked. Okay, so next is Newman projection. So based on where the eye is standing, what is the correct representation of the Newman of this sawhorse drawing? So the clue I told you is if the eye is on the left, so any bond that's gonna be dashed must be on the left. If the eye is on the left, any bond that's gonna be wedged must be to the right of the circle. So you see this hydrogen here must be this hydrogen. This carbon here is this carbon to the front. The carbon to the back, you cannot see it because it's masked by the carbon on the front where the eye is positioned. The circle simply means this circle right here. It simply means there's a bond in between. So now, the hydrogen that I've circled in green should be to the left because it has the dash bonds. The hydrogen I'm circling on the front carbon in red should be on the right and down. Left and down, you see? The shape is like that. Left and down, green. Right and down, red. Look to the back. I have my bromine here. It's pointed up and it has the shaded wedge, so it should be to the right. So that's why it's here, up and right. And then the hydrogen, this hydrogen right here, it must be to the left because it has the dash bond and it's up, so it's this hydrogen. Now the Br on the front carbon is on a regular straight line bond. That means it's on the plane and it's up. The hydrogen to the back is on the plane and down. They are anti. The Br and H are anti-staggered. So that will be the actual Newman projection representation of the sawhorse as drawn. Okay, now 10. Which of the following is the most stable conformation of the chair? Most stable conformation of trans 1-ethyl 3-methyl cyclohexane. Trans means the methyl and the hexyl must be opposite. So this is out because the methyl and the ethyl are on the same side on top of the ring. This is cis. We are looking for trans. Okay, how do I know? This is up, this is up. Okay, this methyl right here is down. The ethyl is trans. Okay, so this is the methyl is down, the ethyl is up. So this is a trans representation. But is it the most stable? The answer is no. The big group is on axial. I just told you want the big group's equatorial for the most stable chair. Here, let's see. Here the metal is down. Here the ethyl is down. So this one is a cis. I wanted to tell you about this because I know I marked this. I regretted this question. This one is a cis. Okay, so we are looking for the trans. So really, this is not the answer. That's why I picked this test so that I will correct this question. This is not the answer. The answer must have them trans, and you want the big ethyl group. You want the big ethyl group equatorial, not axial. So which means this has to be the answer, because the metal is up and it's smaller than the ethyl, and the ethyl is down. How do I know it's down? Look at this bond. It's tipped down. Don't look at the end of the ethyl. Look at the bond directly to the ring. So this is trans, and you have the big group equatorial. So this is the most stable. So really what you needed to be debating between is this ring and the second one, the second structure, and the last structure, because those are the two transes. The first and the third are cis. Those are cis. You have the groups on the same side, either up, up, or down, down. They're on the same side. So you want something that has up, down, and you want one that has the bigger group equatorial. So this has to be the answer, not the one miscircled there. All right. So that is taken care of. Which of the following has the most 1,3 diaxial? Now, I explained why we call it 1,3. The reason is you count from one substituent to the other. Look, you moved from position 1 to position 3. So these guys will, both of them are axials, so they will crowd in space. So really, if you want to answer the question about 1,3, look for the one that has the most big groups axial, either axial up or axial down. That's what you're looking for, because this guy right here has one axial. Okay, we are looking for the one that has the most 1,3 diaxial. Di because there are two groups which are crowding. So you're looking for one that has the most big groups axial, either axial up or axial down. It doesn't matter, or both up and down. All you need is the most axials to answer this question. So this one has no axial. This has the least. If the question was looking for the least 1,3 diaxial, this is what you go for, because this is the most stable chair. Okay, and I think that's it, because all I see is a periodic table. So practice. I hope I've covered much of the concepts available, but I would still tell you to also use your top hat homework questions and the Moodle quizzes. Look at those, and also look at the top hat in-class questions, if any, that were covered that concerns these chapters covered in this test. Good luck.